Hello and welcome. In this video, we'll be talking about the OLS estimator and its statistical properties. In a nutshell, what we will be discussing is in what sense does the OLS estimator work? Now, what does it mean for the OLS estimator to work? Recall that our goal is to recover population effects, to recover true causal effects, but using only a small number of observations, a random sample, not observing the whole population. Now what we're wondering about is in what sense does the OLS estimator computed on the random sample reflect the underlying true causal effects in the population. To give a concrete example of a causal effect, let's consider the setting of young people receiving an education. That means going to school or university. That of course costs money and has an effect on the future of these young people. In fact, as they grow up, they will go on the job market, will find a job, and over their life generate an income. We can formalize this causal relationship by using a linear regression model where we have an outcome variable income that depends linearly on the cost of education, let's call it cost, and also on an error term or unobserved component, where this error term captures all the factors other than cost that affect the income. We assume that the error term is well behaved in the sense that it is exogenous. That means it cannot be predicted from information in the cost variable. For the sake of this example, assume that we even know the values of the beta coefficients. Let's say that the intercept is 40,000 and that the slope is 3. Here 3 is the causal effect that we want to infer from the data. What does our data look like? Well, it looks like an Excel type spreadsheet where we have one column for income, one column for cost, and then we have recorded values for income and cost for different people. Now what is important now is how we get this list, and we assume that this list is generated by drawing a random sample. And by random sample here, I don't mean the concrete realized sample that I will record in my Excel sheet. I mean the plan for data collection. Drawing a random sample means what I plan is that I will randomly choose one person. That will be my first draw. I will record their values. Then I randomly and completely independently of who I chose the first time around, I will choose a second person. So what is important here is the independence between the draws. Once we have the data, we can tell our statistical software to fit an OLS regression and compute the OLS estimate. When we are talking about the statistical properties of OLS, we are not interested at all in a particular data set and the fitted slope on this particular data set. We are more interested in OLS as a plan for generating such estimates. We want to learn in what sense it is a good plan. For example, do we typically generate estimates that are equal to the true causal effect, or at least close to the true causal effect? Since our plan for generating estimates involves in the first stage drawing a random sample, the final number that we compute will also be random. This means that the OLS estimator is a random quantity. Let me give a very simple example of how randomness feeds into the value that OLS computes. We assume that we work with a sample of size 3. So we will draw 3 people at random and we will observe their cost and their income. This is the regression curve. So we draw our first guy, and the first guy has this cost. So to figure out their income, we move up vertically to the regression curve. So this is the income that is causally derived from cost. But then in addition, there are other factors, and what these other factors are will depend on the person. And so for us, they are random because we're choosing a random person, right? Let's assume that randomly we choose a person that has this U and therefore ends up here. If random chance had played out differently, we would have chosen a different person with a different U, and we would not have ended up here. We would have ended up somewhere else. So we repeat drawing at random for the next person. Let's assume their cost is here. And due to their particular U, the final observation ends up maybe being here. And we draw another person, our third person. Maybe they have the same cost as the previous guy, could just randomly happen. But then they will probably have a different U. Let's say they end up here. The fitted regression curve for our sample would look something like this maybe. Our goal is to figure out the slope of the population regression curve. That's the slope of this curve, right? We assumed that it has value 3. Now, in this particular sample, the fitted regression curve is less steep than the true curve. So OLS has estimated a value below the true value, maybe here. Here I've made an argument that the OLS estimate may underestimate the true causal effect. You may not be convinced by this argument for maybe 3 reasons. First, you may not be convinced that these are random points. I certainly chose them to make a point. I didn't choose them randomly. Second, you may agree that a situation like this can occur, but you may think it is rather like a peculiar exception to the rule and not a typical outcome of running an OLS regression. And third, you may think that there's a problem with the small sample size, and maybe this is a problem that can only really happen if the sample size is really small. Let me address all of these concerns now. So what I will do is I will run a computer simulation. That means I'll instruct a computer to generate random samples, and then on these random samples compute the OLS estimates. I do this for many random samples so that I have many examples of what the OLS estimate could look like. To do that, I have to let the computer know what the true population looks like, but the details of that are not really important. What is important is that I'm choosing a sample size of n equal 40, so I'm working with a much bigger sample size than 3. When we look at the simulation results, we can see the little dot that is representing the OLS estimate jumping around, which means that different samples yield different estimates, and some of those estimates undershoot the true value, some of them overshoot the true value. There is randomness in the OLS estimator. Just to recap, the OLS estimator is defined by a random experiment and a rule for computing a value from this random experiment. The random experiment is drawing a random sample. And the rule for computing a value is to take the sample and fit OLS on that sample and get the slope coefficient. To better grasp the maybe unfamiliar randomness in beta 1 hat, it may be helpful to recall a simpler and more intuitive random experiment. Think about the random experiment of rolling a die. And based on the outcome of this die roll, we'll determine whether we have rolled a 1. We record the number 1 if we have rolled a 1 and a 0 otherwise. How do we learn properties of the randomness of the computed values? The answer is almost obvious for the second experiment, and it is we learn through repetition. We repeat the random experiment many times and draw many samples. For example, we first roll a 3, then we roll a 4, and maybe we roll a 1, and so on. We repeat this many times, let's say S times. On each of those samples, we can compute values. A 3 is not a 1, so the value is 0. 4 is not a 1, 0. 1 is a 1. 3 is not a 1, 0. Suppose the property that we want to learn is the probability that the value is 1. That's just the probability of rolling a 1, of course. An obvious guess of this probability is the number of times we rolled a 1 divided by the number of attempts. If S is large, then our guess here and the probability that we're looking for are almost guaranteed to be very close. This near equivalence holds because of a statistical law that is called the law of large numbers. We can use a procedure very similar to this to learn statistical properties of the OLS estimator. This is called Monte Carlo simulation of the OLS estimator. As we did before, we use a computer to generate random data samples. And another one. We repeat this S times. On each sample, we fit OLS and obtain the OLS estimate. To prepare for an appeal to the law of large numbers, we prepare a range of values. So these are values that the OLS estimator could possibly realize to. And now we can ask, what is the probability that the OLS estimator realizes in this range? The law of large numbers suggests that if we run the simulation many times, what we can do is we can just count the estimates that fall into this range as a proportion of the number of simulations that we run, and that will give us an estimate of this probability that will be very accurate if we run lots and lots of simulations. Let's implement this using our computer code to generate artificial random samples. Let's look at our simulation results. On this axis, we have our simulated slope coefficients. Each dot here corresponds to one simulated sample. We have simulated 400 samples, and in every sample there are 40 observations. Since we have simulated 400 times, we have ended up with 400 dots here. The value that we are trying to simulate is 3, that's the population value, the true causal effect. The bars that we see here, like for example this one, represent relative frequencies that tell us how many of the dots have realized in this range. By our previous reasoning, this relative frequency should approximate the probability of the OLS estimator realizing in this range. Therefore, we can interpret this histogram of relative frequencies as an approximation of the probability distribution of the OLS estimator. For us, there are two important takeaways from this picture. First, the OLS estimates are spread out. Sometimes we undershoot, and sometimes we overshoot the value that we're trying to estimate. The variability in the estimates can be summarized by the variance. So at some point we'll have to talk about the variance of the OLS estimator. The second takeaway is that the value that we are trying to estimate sits right at the center of the probability distribution. It even looks as if the expected value of the OLS estimator is almost equal to the value that we're trying to estimate. That's not by accident. In fact, it is true that these two are not just approximately equal, they are exactly equal. That's a statistical property of the OLS estimator and is called unbiasedness. So the OLS estimator is unbiased. Or if you like the definition of an expectation as a prediction, then if you had to predict the value that you're going to estimate, then your best prediction is that you're going to estimate the true value. A caveat to the unbiasedness result is that it only holds if all of our OLS assumptions are satisfied. In particular, it's important that we are sampling at random and that the exogeneity assumption holds.